In this video, I will give you an example of how to work with electric displacement and linear dielectrics. Now, I have the following situation. I have a sphere, and I know this does not really look like a circle, but it's a first approximation. So this is a sphere, and it is made from metal. It has a charge Q, the radius is A, and this sphere is covered with an insulating material that has a dielectric constant of epsilon, and the radius is B. And my goal, what I'm asked to find in this problem, is the potential at the center of the sphere. Now, I do want to remind you, we have solved the problem where I have the sphere with charge Q, but there is no insulator around it, and we found the potential at the center. Now, this is the case where we have the metal sphere, but at the same time we have the insulator around it. I want to first talk about the approach. What are the steps that I will take, and then I'm gonna go on and implement them. But first, I'm gonna give you a big overview of the process. Since my goal is to find the potential at the center, I'm gonna start with that. I know, potential. The convention is that the potential at the point, like the one I'm looking for, is really defined as a potential difference. I want to remind you, there is no way you can measure the potential at a single point. The only thing you can really measure is potential difference. So by definition, or by convention, the potential at the center is equal to the potential difference of the potential at the center minus the potential at infinity. Okay, that's my first step. Now, how do I calculate the potential difference? Again, in general case, I have minus the integral from the initial to the final point of E dot dl. Now, in this case, the initial location will be infinity, okay, because I have minus potential at infinity. The final will have to be the origin, the center of the sphere. So, in order to find the potential at the center, I need to find the potential difference, and that includes knowing what the electric field is. Now, because this is a path integral, this means that I need to know the electric field everywhere, okay, from infinity to the center. I need to know what is the electric field. And if you imagine that you start, let's say, somewhere from here, you need to know the electric field in this area. You need to know the electric field inside the insulator. You need to know the electric field inside the sphere. So, in order to find the potential at the center, I need to know the electric field everywhere. Now, how do I get the electric field everywhere? Before I can get to the electric field, okay, I know that it's gonna be fairly easy to find the electric field inside the metal sphere that is in equilibrium, by the way, and the electric field outside everything, the sphere and the insulator. Now, inside the insulator, that's gonna be the difficult part where I need to do more work, because I know that inside the insulating material I will have some induced dipoles. I will have some polarization taking place. So it will be relatively easy to find the electric field inside the sphere and outside the insulator. Now, my approach for how I will find the electric field inside the insulator will be the following. Because the problem says that the insulator is made from a linear dielectric material, this does make my life easier, because it tells me that the polarization inside the insulator will be proportional to the net electric field in the insulator. So that gives me a relationship essentially between E and the electric displacement D. So in order to find the potential at the center, I need to know E everywhere. In order to know E everywhere, I need to find the electric displacement. And I can do that because I know that it's a linear dielectric, and I know the relationship between E and D in that case. So this will be my approach. And by the way, to finish this, starting, how do I find electric displacement? I can find it if I know the free charges. Now in this problem, what are the free charges? They are not the induced dipoles on the insulator. By free charges, we mean the charges that we place on the sphere. So the charge Q, these are the free charges. So my process will be the following. I'm going to start with Q. I'm going to find D using Gauss's law because I have symmetry. From D, I will use, I can write it here. So from Q, I'm going to find D. From D, I will use the fact that it's a linear dielectric. And this will allow me to find E. And from E, I will find the potential difference. And from the potential difference, I will find the potential at the center. So overall, this will be my approach. These are the steps I will take. All right, and now we can start on our first one. My first step will need to use the free charges and find the electric displacement. Now I will start working on that. I'm gonna write the closed surface integral of d dot dA is equal to the free charges enclosed So now I'm going to apply this. Let's call this equation 1. I will apply equation 1 for points outside the sphere, inside the insulating material, and also inside the sphere. So using I know that the charge is on the sphere, inside the sphere, on the sphere. I know that it's here. This means for any point outside the sphere, the Gaussian surface, and for a Gaussian surface, by the way, I will not draw the entire thing. I will just draw a portion of my Gaussian surface. This is my Gaussian surface. It's gonna be a sphere, a spherical cell. So for any point outside the sphere that contains all the charge, the free charge enclosed will be Q. So this is Gaussian . So the entire charge enclosed will be Q for any R that is greater than A. Now I will assume here, using spherical coordinates, that the electric displacement vector points in the radial direction, and since I need the vector dA, and my infinitely small area vector, the dA vector, will have to point away from this closed surface, and it will also be the magnitude of that, so let's say r, nope, it's a different color, so it will be pointing in the r hat direction, but the magnitude of that can be found by multiplying this side of the area vector theta hat direction with the phi hat direction side of the area. So I will have r squared times sine theta d theta and d phi, and the direction is the r hat direction. So now using these two, the dot product is equal to dr r squared sine theta d theta d phi. And using equation 2 and equation 1, and also actually the result for the right side, which is equation 3, so I will add equation 3 here, combining all of these together. Well, first, no, I'm not going to use equation 3 at this point. I'm going to do the integral first. So using equation 1 and 2, I'm going to have, for my closed surface integral, I need to have theta going from 0 to pi. I need to have phi going from 0 to 2 pi. And this will be dr r squared sine theta d theta d phi. And the integral over theta will give me a 2. The integral over phi will give me a 2 pi. So I have dr r squared 4 pi. Now this is the left side. Combining this result with 3 gives me that dr is q over 4 pi r squared. Let's call this equation 4. Now this gives me the component, the radial component of the electric displacement vector, and I can write it, say, here. So the vector d will be dr r hat, or q over 4 pi r squared times r hat. Alright, so that was my first step. I used the free charges and I found the electric displacement vector. Now I will write my finding again over here. D is, I found D to be q over 4 pi r squared times r hat, and let's make that equation, let's make this equation 5. Alright, now I said once I find D, the electric displacement vector, I'm gonna move on to find the electric field. Now I found D. This is when R, okay, equation 5 is valid so long as R is greater than A. Now I know that D is epsilon 0 times the electric field plus the polarization. Now for R, when R is greater than B, meaning when I'm outside the insulator, of course there is no polarization because I don't have any material. There is no insulating material, there is no dielectric. So this is 0, and this means that the electric displacement is going to be epsilon 0 times the electric field, and using equation 5 allows me to write that the electric field is 1 over 4 pi epsilon naught q r squared times r hat. Now this is, let's call this equation 6, and this is when r is greater than b. Now when r is greater than a but less than b, I do have polarization, and this equation, this expression, definition of the electric displacement is still valid. And in this case, I cannot make the claim that polarization is 0. But I do know, and this is why linear dielectrics are useful, I do know that this insulator is made from a linear dielectric material, and this allows me to say that polarization is proportional to the electric field. And going over the steps that I did in the previous video, at the end of the day you can show that the displacement is equal to the dielectric constant times the electric field. And now if I use the result from equation 5, now I'm gonna get that the electric field when r is between a and b is 1 over 4 pi, not epsilon naught, but just epsilon, the dielectric constant, q over r squared times r hat, and I'm gonna call that equation 7. So I have found, for r greater than b, I found everything. For inside the insulator, I also found the electric field. Now I need to work on when r is less than a. Now we have to remember that this is a metal sphere. An important property for any metal object in equilibrium, the charges are free to go anywhere they want, and for a metal in equilibrium, the excess charge will always be found on the surface. So all of the charge Q is going to be found, the free charge Q is going to be found on the surface, which means if your Gaussian surface has a radius r less than a, and you apply Gauss's law for the electric displacement d, your right side is going to be 0 because there will not be any charge enclosed, which means your displacement is going to be 0. Now we are talking about a metal, of course, there is no polarization, and we know that for a metal in equilibrium, the electric field inside has to be 0. So what I was looking for from all of this work is the electric field. Let's call this equation 8. So I have 3 expressions for the electric field. It is 0 when you are inside the metal sphere. It is 1 over 4 pi epsilon q over r squared r hat when you are inside the insulator, and it is 1 over 4 pi epsilon naught q over r squared r hat, exactly the same as if you had the point charge at the center of the sphere and you were using Coulomb's law to find the electric field. So I have the electric field. Now I can do the path integral to go from infinity to the center of the sphere in order to find the potential there. And this is how I will proceed. Alright, let's move on to finding the potential difference. So I'm looking, I need to find V naught, which by definition is V naught minus V infinity. So I got minus the path integral from infinity to O, the center of the sphere, of E dot dl. Now, starting from infinity and going to the center, I'm gonna pass through three areas. The area that is outside the insulator, the area where the insulator is, and the sphere. So what I will do, I will break this integral into three pieces. I'm gonna go from infinity first to r equals b, and then I'm gonna go from r equals a. No, I'm gonna go from r equals b to r equals a of E dot dl, plus the last one, I'm going to go from r equals a to the center, and I need to calculate E dot dl for that. So I got three integrals. Now, I did mention I found the electric field inside the sphere to be 0, so I'm very happy I can say that that last integral goes to 0. Now, since this is a path integral, okay, I have to choose a path to calculate it. And the path that I'm going to choose, I'm going to start from infinity. Let's say here is infinity, and I'm gonna go to I'm gonna take this path to go to the center. Because I'm following this radial path, I will make the claim that my dl vector will only include dr r hat. I'm never going to move in the theta hat or the phi hat direction. So that's my dl, and I know that the electric field also points in the r hat direction. So I'm moving on. I got minus, going from infinity to b. The electric field vector here, I found it to be 1 over 4 pi epsilon naught q divided by r squared r hat dot product with dl, and as I said, for dl I'm gonna use dr r hat minus, now I'm going from b to a, of 1 over 4 pi epsilon. Okay, pay attention, this is epsilon, not epsilon naught. This is the dielectric constant. Q over r squared, again r hat dot product with dr r hat. Now remember, because I have r hat dot r hat, this will give me 1. Okay, you have to remember this property of unit vectors. And if you had written dl as all of these three components, the r hat, the theta hat, and the phi hat, they would when you would do r hat dot theta hat, you would get 0, because these unit vectors are perpendicular to each other. So you could have written the dl vector in the general form in the spherical coordinates, and you would still get rid of 2 out of the 3 terms. The only one that would survive would be the r hat dot r hat, and that will give you 1. So my integral is minus infinity to b 1 over 4 pi epsilon naught q over r squared dr minus, going from b to a, 1 over 4 pi epsilon q over r squared dr. Okay, so now this is the result of these two integrals. You will give you the potential at the center of the sphere. So this will give us, if we take out q over 4 pi as a common factor, 1 over epsilon 0 times b plus 1 over epsilon times a minus 1 over epsilon times b. And this is the potential difference v naught minus v infinity, v center minus v infinity, which is by definition the potential at the center of the sphere. Now, for the integrals, this is a simple integral, the 1 over 4 pi epsilon naught q, that's a constant, you can take it out, and you have dr over r squared. So you will have the function whose derivative gives you the 1 over r squared will be a 1 over r function. So you can do this simple integral and you will arrive at this result for the potential at the center of the sphere.